Hello everybody, my name is Petr Gábrlík and I'm PhD student at Brno University of Technology, which is actually also in Czech Republic like this university but in different city. My talk will be not so scientific, it will be a little more about applications in my research group. So I would like to start with few details about my research group. So the university is about 2 hours east of Prague, like by car or train, and it's probably one of the biggest technical universities in Czech Republic. So we have a similar structure like here. There are faculties, there are departments, and I'm part of the Department of Control and Instrumentation, and there is a group of robotics. So, yeah. We are quite a small group. We are about 10 or 12 active people, and our group leader is Professor Žalud. And the size is quite similar like this MRS group, but our objective is, or focus is a little bit wider. So I would like to talk about our applications and research, but at first maybe I would like to mention one of our products. It's Orpheus AC. It is a Reconnaissance robot designed and developed or constructed for military, Czech military, for chemical unit. And actually this robot is quite interesting, but not too much in terms of this summer school, because it's just remotely controlled. It has chemical sensors, and so it just has to work in a wide range of conditions. But the military branch is quite conservative. They don't like, or they don't want slams or autonomous trajectory plannings, and so. So we are mostly work in a civil scene or civil area. Our focus is mainly in field robotics, ground and aerial as well, biomedicine, industrial robotics, and we also cover some tasks from automotive. Let me shortly talk about one of our applications, about one experiment. Actually, we like CBRN tasks. It means chemical, biological, radiation, nuclear tasks or threats. And I would like to mention our experiment. So just imagine we have an area like this one. It's about 1,000 of square meters, and you don't have any prior knowledge about the area. You just have such Google Maps orthophoto. And you know that there was potential accident, and maybe there is a radiation contamination. So our approach consists of 3 phases and actually 2 vehicles. We use aerial platform and a ground platform, and there are 3 phases. At first, we create an aerial map using UAV, using a photogrammetry technique. In the second phase, we switch the equipment on the UAV for radiation measurement. And the third stage is focused on ground radiation mapping. So I will show you how it works step by step. Yeah, this is the area, and this is an initial flight, initial trajectory for the UAV flight. It's just a common trajectory to cover, to do a photogrammetry. Yeah. The UAV is equipped with a multi-sensor system for the photogrammetry. It's equipped with the well-known RTK GPS, and it's able to produce really precise orthophotos and terrain models. So they are the actual photos positions, and this is actual orthophoto. You can see there are some changes, like in this area, there are some vehicles, and there was an accident probably. And here is the digital elevation model, the 3D map, let's say. Now we can clearly see that part of the region is quite hilly, second part is quite flat, so it will be interesting for the navigation of ground robot. But at first, we use this map, this 3D map, to perform the second UAV flight, which will be focused on aerial radiation mapping. So we used the knowledge about terrain shape, and we designed a trajectory which we just fly just above the ground, about 10 meters above the ground level, to obtain very homogeneous results of the radiation measurement. As a result, we have data like this. Now you can see there are some increased levels of the radiation, and after some automatic processing, we obtain this result. There are two hotspots. The data from the aerial radiation measurement are interpolated and then filtered, and a few other steps. But we defined two hotspots, which are where is the radiation level higher than the background. In the next step, we combine these hotspots, these polygons, with the obstacle map derived from the digital elevation model. As you can see now, the red polygons are a little bit adjusted according to the black parts of the map. The black parts are the obstacles. It's not, they are not just obstacles, there are also steep slopes which are not cannot be covered by the ground robot. So for the ground robot, also the steep slope is an obstacle. So we have adjusted polygons, and now we can deploy a ground robot. Here you can see design trajectory to cover just these two small segments, two hotspots, and after the ground robot finished the processing, and after some processing, we obtain again radiation maps, but just maps of the small polygons, and these maps are logically more precise. So this is it. This is the detail of one of the area. You can see that the ground robot can write about obstacles, and in the middle there is a barrel with one of the gamma radiation sources. This is it. This is a small animation. You can see the 3D model combined with the radiation levels measured by the ground robot. So this is a 3D point cloud with texture combined with the other layers. All our data are georeferenced. Actually, we use RTK GNSS on board the drone, also on board the ground robot. So that's all from my side. This is kind of our field work or field camp, and yeah, thank you for your attention.
Thank you, Petr. I will ask Radosław to be prepared because we don't have more time. And in the meantime, if you have some questions, so if there is no question, thank you again. And Radosław will tell us something about his company, I expect.
Hello, I'm Radosław Grymin from Wrocław University of Science and Technology. I'm also working in Spirosoft Solutions SA as an artificial intelligence engineer and roboticist. In Wrocław University of Science and Technology, I am doing my PhD on discrete and continuous optimization problems. And in Spirosoft Solutions, we are doing autonomous driving for very big German company. Unfortunately, I cannot say which company is it and which algorithms we use. But I will try to focus what I'm doing during my PhD. Currently, it is UAV inspection. In our company, it is autonomous driving car project. So I will tell about project assumptions and my current responsibilities, which problems I solve there. And also about some project about optimization in architecture that I am doing with Judita Cichocka from MIT. She's doing she's studying structural engineering there. So without further ado, I would like to go to UAV inspection and my PhD problem that I'm solving now. So the general problem that I solve is that we have some areas A1, A2, A3, A4, and for each area we can define each area is an area from that we can do very good legible photo of object. A1 is an area from where we can do a legible photo from object O1. A2 is an area that we can do visible photo from object O2, and so forth. So we start inspection P0, start inspection from point P0, and we would like to find points P1, P2, P3, P4, from which we will do this inspection. So first problem is to find points P1, P2, P3, P4, and second problem is to find the permutation of these points to minimize objective function. Currently, we are using the distance, so we are minimizing the distance. So it is it is actually the same as this Dubin's problem that was showed yesterday by one of the lecturers. And we are looking for effective meta-heuristics that will solve this problem. I saw that we found out that if we use this Dubin's airplane model, that generated path comprises straight lines and arcs, some jerks will happen when we follow this path, because when we go straight and then we would like to start turning, when we enter this arc, there is a problem that some jerks generate. So we would like to use some clotoidal curves to allow this UAV to pass smoothly through this path. So currently we just solved it very easy as a two-layered optimization problem. One layer is one layer is discrete. This is high-level procedure, and there we use to opt and simulated annealing. And low-level procedure is continuous, so we use Powell's algorithm. So we have to first of all we find the permutation. For this permutation, we are looking for the optimal points. And then when we have the optimal points, we can check once again for the permutation and switch these algorithms to find these points where we visit these circles. And then we will try to modify this path to make it smooth, make these properties of this path good for driving, good for example, VTOLs, vertical takeoff and landings vehicles. So next thing is this autonomous driving car project. What are the assumptions of this project? Our goal is to create the autopilot that our customer will sell to the other car companies that will satisfy requirements for this fourth autonomous level. What does it mean, fourth autonomous autonomy level? It is how high automation this car will drive autonomously with limited conditions. So if some conditions will be satisfied, this car should work totally autonomously. There will be some safety driver, and if these conditions stop happening, if they changed, this car will release control to the driver. And our technologies are top secrets. I can also tell you that Tesla has second level of autonomy. And our main goal is to find the path and to find a good optimizer that will well converge, almost always converge, because it is also a problem, global convergency of these path planners. And third things, optimization in architecture, why design problems are difficult. We have large design space. Simplified problems is useless. The objective function is noisy or varies with time. Problems that use architects are heavily constrained, and sometimes it is non-intuitive. And they have a lot of objectives. Yes, and these objectives are very commonly conflicting. For example, we want to satisfy some objective, and simultaneously we would like to use less material.
Sorry, please go to conclusion.
So we created the solver that we can put in Grasshopper. We can, for example, show some problem. It is the restaurant in Mexico, and such solvers can optimize these optimization variables like height, width, and overhang. And then we, the designer, when runs our solver, can see the Pareto fronts and see how does look like design connected with each solution. So we had we were distinguished also at MIT in machine learning across disciplines competition in 2019. Thank you very much.
Thank you, Radosław. I will invite Elliott to prepare his talk, and we have this time for question. So do you have question for Radosław? If not, let's continue with the second presentation. Sorry that I was so strict with the time, but you know, we have dinner today, so I want to be on time.
Hello. So hi, I'm Elliott. I'm from the University of Bristol in the UK. So I work in the swarm group that they have there. So I'll be talking about the work I'm doing in my PhD on human-swarm interaction. And this should link in quite nicely with the talk we had before, which is very interesting. So obviously we're all very interested in thinking about what do we need to do to deploy real-world swarms and multi-agent systems, you know, for all these kind of different applications. And we've seen a lot of interesting work about how we could do that. So human-swarm interaction is essentially just one way we could think about doing that. So essentially, rather than thinking about we just have a completely autonomous swarm that we deploy and it just operates completely by itself, we in fact have, you know, a human in the loop. And this is beneficial basically because, you know, as a human we have very high-level reasoning for, you know, we're very good at planning things and observing the state of the world. And when we think about swarms, they're very reactive, but this means we actually have very simple swarm agents, and they're not exactly very clever. So you could imagine a scenario where you have a swarm for a search and rescue scenario. You notice that the swarm is actually going into an area that you know has already been explored by a manned team. Your swarm's not going to be able to understand that. So having a human that can, you know, understand this and then convey that to the swarm is actually, you know, very useful. So one of the problems with human-swarm interaction, though, is that, you know, we have all of these different kind of tasks that we can have the swarm do. It could be foraging, you know, search and rescue, all these different kind of tasks. We could have different swarm sizes. How do we allow the human to control the swarm? What are the communication limitations? How well trained is the human operator? So you see you have all these parameters that you could change, and we want to ensure high-level performance, and we want to know with some confidence that the system we configure is going to achieve that. And that's hard to do with human trials. So what I'm doing is actually looking into, rather than have human trials to show how we control swarms, is actually evolving behavior trees. And essentially you can think of a behavior tree is just a way of representing some sort of decision-making strategy that could be used to infer some knowledge to the swarm based on its state. And through artificial evolution, which is basically just a type of reinforcement learning, you can very rapidly create optimal solutions. And this is great, because then we can, you know, do lots of these simulations very quickly, as opposed to human trials where you have a very small window and you have to take a long time to, you know, get ethical approval. So it's just some of the initial work I'm doing is a very simple kind of search scenario where you have a swarm exploring different environments and different places for targets. And the idea is that the evolution will minimize the time to find these targets in these different positions. And I allow these kind of behavior trees. They can observe the swarm by looking at the center of mass and the density. And then through that can decide when to make certain actions. And the kind of actions that we might want a human to take is, okay, let's change the different emergent behaviors that the swarm can deploy. So that might be dispersion, or here I have kind of different kinds of directed flocking. And then through that, you can very quickly, so we're kind of good at Bristol, we have a supercomputer that we can run lots of simulations on. So these, the kind of, you know, you have 3 different environments, and then I can change all the different target positions, and we can observe, you know, what are the different swarm behaviors that emerge. And then we can think about, okay, what does this mean about the way we think about designing these systems? And we can really identify that even for simple scenarios, once you start changing the conditions, the type of optimal behaviors that evolve change kind of dramatically. So this is just showing, you know, one scenario and one evolved solution. So that's the behavior tree at the top, and this is showing how it actually operates in real time. So it's observing the center of mass of the swarm and its density, and it's changing the actual actions it wants the swarm to take. And this makes a very nice optimal way of exploring the environment. So this is a very kind of foundational work. So we can show that we can do this for different kind of environments and different targets, and we can then observe, okay, how does this make us, is center of mass a more useful way of representing a swarm? Is density very useful or not useful? And you can see about what are the preferred types of actions that could be made, and then we can use this for when we actually design these systems for the real world, and think about what kind of actions and representations we might want to give to a human to control a swarm. So yeah, so that's very kind of only my first year. So I'm now looking into more kind of complex scenarios where you might have floor plans of buildings, and then looking into things where, you know, you have like real world communication limitations, and thinking about how that might change the kind of strategies you want to implement. So yeah, thank you very much.
Yes, thank you for short presentation. So we have time for questions. Yes, can you try to tell the question?
Yeah. So the behavior trees can change the emergent behavior that the swarm deploys. So I showed very quickly that you could have dispersion. You could say flock north, flock south. Basically flock in any direction you want. And that's just one way that you could have. There's lots of different ways of kind of doing human swarm interaction. So one way is that you can actually manually take over control of one agent. Then through that you essentially, we talked a lot about leader follower stuff, and then you act as that leader and change how the swarms behaves to your design.
Thank you. So please, Minhoe, could you tell us something about your research?
Hi everyone. I'm glad to present my work. Actually, I don't work on the robotics, but as the title says, I work on the machine learning and wireless communications. But I work on the decentralized wireless communications, so it has a quite common ground with decentralized decision making in robotics. So you may have this work might not be fall into your research exactly. However, you can take some messages away from this talk. So this work is with Paul Decker and David Jespert from Euroconference. So the resource allocation is a very old optimization problem for maybe all other fields, including the wireless communications. So in order to solve the resource allocation optimization problem, there has been some approaches with machine learning, and these are some state-of-art machine learning, deep learning based resource allocation schemes. And I'll just skip it to directly to the problems. So this is a sum rate function for wireless communications. So it can be sum rate, or it can be energy efficiency, or it can be any other utility functions. And here in these wireless communication problems, there are k users, k pairs of transmitter and receivers, and they are trying to communicate each other, and they consider all other signals from the signals from all other transmitters as interference. So which means that this problem is non-convex, and it's NP-hard problem. So it's hard to solve. If we look this problem as a decentralized case, then we can just generally say that each pair has a partial observation to a system state. So let's say this G is a system state. In wireless communication, it is channel state information. And this pair 1 and pair 2 have partial observations at their local location. However, there might be some errors. So this pair 1 has an error of error in their estimate. So instead of 2, it observes 5. So there's an error in here, and this in user 2 there is no error. So because of this error, user 1 thinks that the optimal solution is 0, 1, and so it has a power it transmits power 0. And user 2 thinks the optimal solution is 1 and 1, so it transmits the power at the maximum level. And this makes the sum rate 2.0. However, with the perfect CSIT, you can get the 2.3, which is much larger than, not much, but larger than the 2.0. So it means that because of these partial observations, it is hard to make decisions. So this is just without the information sharing scheme. So in each TX, each agent, it is trying to make a decision with your network. So I added up the information sharing from the pair 1 to pair 2 and pair 2 to pair 1. So there's information sharing between the two users. So this is just an example of a scenario, and this user has user 1 has a noisy sigma, and this user 2 has a perfect access to the system information. So what happens here is that with this information sharing from each other, it can get a perfect sum rate, even the noise is getting very large. The other case, there's only message sharing from user 2 to user 1, and it achieves still the same. And the direction of the message is now changes from noisy user to the perfect user. So from noisy user to perfect user, because noisy user doesn't have it just has a noisy information about the system state, so there is some degradation. And if we compare with the scenario where there is no sharing, of course the sharing some information with each other helps to improve the performance. So we can say that it's better than more informed user. It needs to share to the other. So just forget these details, but it's just it means that this graph in the y-axis, it means the message is equivalent to P1. If this is 1, then the message is same with the decision of P1. So it means that this perfect user is sharing the message, then it tells the other what to do. So in this message, it contains the information that what this user 1 should make a decision as. And if you see this, the second graph, it means the mutual information between the message and the decision. It means that more information has been delivered to the user 2 to user 1. So it's as noise increases. So as user 1 lose the information, it needs to be told by another guy who has the more information. It's the other case in here. Here, if we look at this message and the decision between the relationship between the message and the decision here and here, and this it means that the P1 is equal to the message. It means that this user 1 is sharing its own decision to the other. Because this user 1 has noisy information, it cannot tell the other what to do. It just tells its own information, and based on this message, this user 2 with the perfect information is making the good decision based on the message. So this is just a graph that shows that it outperforms the conventional algorithms. And just takeaway message is that it's very difficult to learn what in the decentralized policy with many users. So you should share your information so that your own whole team can make the best decision. And as I said here, I forgot to tell all the decision maker and the message maker is composed of neural network. So which means that machines can learn by itself what to share and what to decide. Okay, so this is the end of my presentation.
Thank you. Let me ask another presenter, and if you have some questions. No questions, so thank you again, and please continue.
So, hello everyone. So I'm Jonas. I work at the Iridia lab in Brussels. So we are not all working on the same thing, and the work that I'm presenting is actually one ERC funded project. We have other projects, for example, bringing together blockchain and swarm robotics, or the construction task that you have seen in the presentation of Heiko earlier. Those are also conducted in our lab, so it's not just what I'm doing, but we're doing many things. So, but I'm working in the automatic modular design for swarm robotics, and I'm going to give you a short introduction on what this is, and I'm going to present my results only shortly because I think you can take more away from our philosophy than what I can present in my own results. So we already had the introduction to swarm robotics. So as Robot Swarm is a multi-robot system that operates decentralized and autonomous and self-organized. It has benefits, or at least postulated benefits, of fault tolerance, scalability, and flexibility. But there is one difficulty, and that is that it's very hard to design the control software such that the desired behavior of the whole swarm emerges. And that is good for us, because we are hired as PhD students, researchers, and so on to solve these problems. But on a global scale, this is a problem, because not every company that wants to deploy a robot swarm wants to hire a PhD for 4 years. They want to have the results a little bit quicker. And thus, many people turn to automatic methods. One very popular one is evolutionary swarm robotics. So you take an evolutionary algorithm, you let it evolve, usually an artificial neural network, and you can solve a wide range of tasks with it. So moving while holding a formation, division of labor, which we have seen earlier also, or simply abstract collaborative tasks, which then can be replaced by whichever task we actually need. There are a couple of drawbacks. So even though this is automatic, it's not always competitive with somebody who has the experience and designs a swarm behavior by hand. Then the design process itself needs to be tuned for every task. So what I'm saying here is that alone for these 4 tasks, you need to hire at least 4 people trying to solve each of them on their own. So you cannot just say, okay, we can divide labor. Now I would like to also solve a collaborative task. You need to tune your design process again. And the reality gap, that is the difference between simulation and reality, is actually quite hard. This is because evolutionary algorithms are really powerful. And they just take every feature that your simulator gives them and tries to optimize it. And if you do not match reality 100%, that is going to fall back once you put your robots into reality. So what we're trying is in machine learning, there is the so-called bias-variance trade-off that you might have heard of, and we're trying to do the same. We're introducing a bias in form of creating modules which are handcrafted, and then we're using an optimization algorithm to generate control software out of this. And depending on how much bias you need, so how much initial information you want to provide to this design process, you can craft very high-level or very low-level modules. So 2 proof-of-concept methods were Automate Vanilla and Chocolate, and the Automate approach exists in many more flavors, where we take a set of 6 behaviors and 6 conditions and combine them in a finite state machine. The states execute a behavior, the transitions in the finite state machines are triggered by the conditions, and even though we are worse in simulation than an evolutionary algorithm, we do beat them in reality. So I think this is a big plus, and it shows that this approach actually works. So what I have been doing is we have been taking the behavior trees, which you have heard about earlier, which are just another control architecture, and we have been adapting them. The great benefit of them is that they are modular by design. So you have the conditions and the actions at the bottom, and these are our behaviors and conditions that we already had defined before. So we take this kind of architecture, which is then closely related to the finite state machine that we had before, and we were shown that also behavior trees are as performant as finite state machines in this modular approach. There is, however, one restriction, and that is that our optimization algorithm was probably not very well suited for the behavior trees. So that is why we're then looking into using local search techniques. These are borrowed from the optimization community, so iterative improvement, simulated annealing, taboo search, or iterated local search as candidates for that. And we are pretty sure that we can actually improve the performance of the behavior trees when we're using this. The first results are already looking promising, and yeah, so that's, okay, so if you want to look at all of this nice papers that are related to this, I have included them here. Thank you very much for your attention, and any questions?
Thank you for the overview. Again, I will ask another presenter, and in the meantime, if you have some questions. Yes, if there are no questions, thank you again. And Martina will tell us something about her research in Salerno.
Okay. So good afternoon. I'm Martina Lippi from the University of Salerno in Italy. And today I'm going to introduce my PhD activities that are concerned basically the human multi-robot interaction. So my research activity, okay, can be basically decomposed into two main subtopics. There are the distributed control of multi-manipulator systems on the one end, and the human-robot interaction on the other end. And concerning this aspect, it is possible to identify two main scenarios. There are basically the workspace sharing, where we have that robots and human operators coexist in the same environment. And in this case, the objective is to guarantee mainly the human avoidance, whereas in the second scenario we have a physical collaboration between these entities that generally is performed by means of a shared object. And in this case, the objective is generally to provide human assistance or to have shared control. That means that we have autonomous behaviors of these entities that must be somehow combined. So the advantages of having these entities collaborating with each other are that it is possible to combine the major reasoning skills of human operators with the major physical skills of multi-robot systems. And in the case of distributed architectures, there is also an increase of flexibility, scalability, and robustness to faults with respect to centralized architecture. But the problem is that then arises is that the human behavior is unpredictable by nature, and this requires to adapt the robot's behavior in a dynamic way with respect to the human behavior. And in doing so, it's also necessary to always guarantee that the replanning strategy is compliant with the constraints that may be introduced by the multi-robot systems, such as the presence of closed kinematic chains. And of course, this, the need to guarantee this compliance is even more challenging in the case of decentralized control architectures. So the first scenario that I considered is the case of workspace sharing. So there are these entities that coexist in the same environments, and here the example is just with two robots, but they can be n robots. And the basic approach first tries to assess the human level of safety with a safety index, and to this aim first, the safety index with respect to a single point of the robot is defined, which takes into account the relative motion of the human operator and the robot. And then it is extended to every point of every manipulator of the team. So once this safety index is defined, the objective is to modify the cooperative trajectory in order to guarantee that this safety index is always greater than a minimum value that can be time varying. And for this purpose, a trajectory scaling approach has been considered, which allows basically to preserve the nominal path of the robots while modifying only the time law on this path. And here the basic idea is to introduce a new time parameter, C, and to parameterize the nominal trajectory with respect to this time parameter. And then this time parameter is then is actually scaled in order to guarantee the safety condition. So once the reference trajectory is defined, is obtained with this scaling procedure, this must be also tracked by the multi-robot system in a distributed fashion. And for this purpose, a leader-follower approach has been considered, where basically the leader computes the new reference trajectory, and this is estimated by the follower robots. And in order to track this trajectory, local observers are introduced, which allow to estimate the overall safety index, since it depends on local information of the robots, and the reference trajectory and the overall state of the system. And this approach has also been validated with a dual arm setup, which is composed of two Comau Smart 6 performing a cooperative transportation task. So here, basically, the trajectory is modified according to the motion of the human hand. And when they move towards each other, we see that the trajectory is scaled down, like in this case, and the safety index is basically saturated to its minimum value, and so on. The second scenario that has been considered is the one of assistive physical interaction, where there is an exchange of forces between the human operators and the robots, and this is performed by means of a common object. So here, the approach is that we first define a virtual dynamics that we want to impose to the object. And this dynamics is basically a mass spring damper dynamics, which allow to have a compliant behavior on the object that is generally desired in human-robot interaction. And this dynamics depends on the human branch regulation error. So we assume that we define a desired human branch, and that can be 0 in order to minimize the human effort. And the objective is to design this reference trajectory XR, which allows to have the convergence of this regulation error to 0. And so then the objective is to define this reference trajectory, and to this aim we assume that the human branch can be modeled as a spring with unknown and time-varying parameters, and robust and adaptive control theories are adopted in order to define this reference trajectory. In the end, once this virtual dynamics is defined, the objective is, of course, to actually impose these dynamics to the object. And to this aim, again, a leader-follower approach is used, where the leader estimates these, evaluates these virtual dynamics, and then the followers estimate it. And local observers are used in order to estimate the desired virtual dynamics, and in this case also to estimate the external forces that are exerted on the object, that are the forces actually exerted by the human operator on the object. And because of the tight cooperation, in this case of the robots, there is also control of the internal branches that may arise during this cooperation. And this approach has been validated on a simulation setup, which is composed of 3 Kinova mobile robots. So in conclusion, solutions for both workspace sharing and the physical human multi-robot interaction have been presented, and the future works aim at validating the last approach on a real setup, and at extending it by also including human prediction techniques. And other works that I didn't mention concern the cooperative object transportation between by multiple aerial and ground vehicles, and techniques for distributed fault detection with mobile manipulators. Thank you for the attention.
Thank you, Martina. Do we have some question? If not, let me ask Federico. Yes, please tell us something about your computer vision approaches.
So, welcome everybody. I will shortly introduce my work for the master thesis at the University of Rome. So we have known a lot of ways on how to deploy a swarm of robots to cover and map an environment. Now we wanted to see how we can use this swarm to actually improve our sensor capabilities. So we have used to we have chosen this task in the precision agriculture. So we have to a crop field in which we wanted to map weeds and crops so that we can use a targeted application of pesticides. This is the main context of this project. You can refer to these two articles if you want further details. So basically, each agent is performing a random walk in which is attracted by other agents activating beacons in which areas are not yet mapped or in which the confidence we have about this area is not that high. And on the other time, another way, they are also repulsed by others so that we cannot converge to the same area so that the coverage of the environment is guaranteed. What we need to apply computer vision algorithms to this swarm, we need a lightweight object detection algorithm. It has to be, of course, reliable, and it has to support the collaboration between the agents. Well, we can skip this. So beside this, with the group of the La Sapienza University, we are developing a simulator for precision agriculture. We have used Unity, which is a popular video games engine. Advantages, it can be connected with ROS, so you can just do your stuff in ROS and then use the simulator only for the visualization, so that we can achieve a better realism of our environment. So this is an image again. This is a paper in which they explain how to generate the fields starting from 2D textures. So I can skip this. So we have used FastRCNN, which is a really popular and deep architecture. So basically, we work on the CNN blocks to get it shallower. But in any case, so this is we have used the shallower network, so it's just a 5-layer convolutional neural network in which we can input the images together with the previous knowledge we have about the field. So at the beginning, we want to see where to deploy our agents. So supposing that we have multiple agents fly at high altitude, we can apply a standard half-transform method to easily extract areas of the fields in which weeds are more likely to be. And from this, then we can deploy the other agents to the closer inspection to have a high resolution on the image. So this is the main approach. We have no knowledge about our field, and we perform a plain RGB detection. After that, we can compute a probability map in which we encode our confidence about the fields in the given areas. And this process can go over and over until we see that our task is achieved. This is basically what we achieved in our results. So as you can see, you have two dashed lines in which we compare two different architecture, one with 5 layers and one with 9. And the box plot instead represents how our performances grow over the time. So we have seen that given the right balance in the training set, with a 5-layer network, we can achieve the results of a double-sized network. So well, that's all. Thank you.
Thank you for being on time. Do you have some question? No, so let me ask Sebastian to tell us something about ant colonies optimization.
Okay, hi. So I'm trying to go quick because everyone is hungry, I guess. Yeah, I changed the title a little bit because I thought I was faster in research and could present some results, but I was not fast. So I only can present to you some idea. First, a little bit about me. When I was a bachelor student, I got to the Swarm Lab in Magdeburg, and I didn't start to do research in swarm robotics, but I actually started there building robots. The robots you see there, and you see that there's actually quite different robots. That's because there is different generations and they evolved over time. But now I'm at my PhD and at my first year of my PhD, and I ditched the quadcopters, so don't blame me, but I'm working on different robots now, and I talk about that later. But our group, there is not many people doing robotics in our group, so I'm pretty much the only one doing robotics, and most other people in my group do swarm intelligence and optimization, and I try to use robots to implement their ideas in real robotic applications. And I have worked a little bit on localization, and I've worked a little bit on collective search on the theory side, and now I'm looking into planning and foraging. And yeah, I said that I use different robots now. This is the robot. It's called Turtlebot, and I use those robots because they have a laser scanner and they can map their environment, which I guess out of swarm robotics, most robots can do something like this. Inside of swarm robotics, pretty much no robot can do this, and I don't know why we should use different robots than everyone else. And currently I have a bachelor student who tries to implement virtual pheromones, and yeah. Here you can see some pictures that's from another group. They use kilobots to do foraging with virtual pheromones, but they use augmented reality to get their pheromones. And we try to do the same thing with onboard sensors, and we have copied their behavior basically and used our pheromones. And there is a problem because we used the navigation stack from Ross, and if you do this, then the robots coming from the nests run into the robot coming from the food source, and they do what you do when you meet someone in the hallway. You come, you see, oh, I need to go to the right, and then he goes to the same direction, and then you go to the left, and he goes to the left, and you wiggle, and they are basically stopped, and I think that's stupid. They should be able to communicate their plans and then plan around that. And this works in real collectives, right? The sheep don't run into each other, despite they still maybe know where they want to go. And the question I am asking is, if everyone does his own planning and you communicate your plan to your neighbors, then what kind of a global plan emerges? What should you communicate about your own plan? And how can you integrate the information about the other agents' plans into your own plan? The idea is to use uncollinear optimization for that. So you have a pheromone map that kind of represents your plan, and you can communicate this pheromone map to your neighbors. And the second approach I use is cooperative coevolution, that allows me to co-evolve the plans of the different agents so that they fit each other in the end, and different constraints are met, like there should be no collisions and stuff like that. Okay, I'd love if you talk to me about that and give me even more new ideas. And with that, I'm done.
Thank you. Some questions? We are going really fast, so the motivation of brewer is strong. That's great. So we have the last presentation. It's going to be on the screen. Perfect. Thank you.
Okay. Hi, so my name is Yoni. I'm from the Autonomous Drones Lab in Tel Aviv University, and I'm going to talk a bit about SLAM. So, as you know, uh, implementing SLAM is not so easy, and it's even harder for drones. But what do you need SLAM for? So, just a second. So, let's say that you just wrote a new paper with a cool idea, and you would like to test it and to demonstrate it in the experiments section of the paper, and you would like to do it with a real drone and to use SLAM with no motion capture. Why? Because then you have a better chance to get your paper accepted. So we give you a set of tools of platforms to implement your SLAM. You can see here. Let's see if this works. You can see here the Qualcomm Flight Pro, the Crazy Flight 2, the Bebop 2, the Jetson, the Intel T265, and we implement all our SLAM algorithms on ROS. So let's see. So we printed a small 3D printing for the drone on which we install the Jetson, and let's see a short demonstration in which we implement Hogg SLAM on the Jetson Nano.
In this work, we demonstrate an autonomous robot running Orb SLAM 2 for state estimation on board a Jetson Nano. No external position tracking is used. The video, received through Wi-Fi from the Bebop 2 drone, is processed on the Nano at approximately 8 Hz using the Orb SLAM 2 algorithm. The output of the SLAM algorithm is used for closed-loop control and sending velocity commands back to the drone. The drone's movement is relatively slow due to the current implementation on the Nano. We are currently working on realizing more parts of the algorithm on the GPU, thus increasing the total frequency of the position control. On the right side of the screen, you can observe the map constructed in real time and the drone location within it, seen as a green moving rectangle.
And here we we printed a small print for the small camera, and we installed it on the Crazy Flight 2. In this movie, you can see again you can see again that the SLAM is being done in real time. You can observe that the drone is very stable, and this is due to a low communication delay. And another way that we give you to implement SLAM is with the same drone, but now we install the T2 65 here, and we use the Raspberry Pi running ROS to control the drone. And one last option is to use the Qualcomm Flight Pro. We are going to release all the code in ROS to control all of the platform that you just saw soon on our GitHub of the lab. Thank you.
Thank you. There is one question.
Yeah. Yeah, it's on board. We haven't put the part that we printed on the drone, since it means that the drone is going to fly only like for 1 minute. But in the next version of the Nano, it's going to be like about half the weight, so it would be a lot easier to actually install it on the drone for 3 or 4 minutes of flying. Okay, so we implement the control loop on the Raspberry Pi, and we command the drone according to the result of the control loop. What again, please? We change it a bit in order to fit both to the specific hardware and to the specific cameras that we used, but most of the SLAM stayed as is. Yeah.
Okay, thank you again.
Thank you.
Yes, so we are perfectly on time. So please, I hope that coffee break is ready already. But if it's the case, please refresh yourself and let's meet here after like in 15 minutes.